Hello. In the last several classes, we have looked at solar energy and wind energy. We focused a lot on those two because they have considerable promise, and it's something that you can install easily, relatively easily, and you also see it considerably in it's quite visibly there in many places around the world. And people also consider those two to be quite promising in terms of the ease with which they can be deployed, the number of places they can be deployed, the flexibility of these technologies and so on. So, that is the reason why there was so much focus on it, and there is so much information also available on it and so on. Today we will look at another of our renewable energy technologies that people have worked on to differing degrees of success, and that is the ocean thermal energy conversion, or OTEC. It's as it's called, ocean thermal energy conversion. As you know, 2/3 of the planet is covered by water, and clearly if you have energy there which you can tap, that is a significant amount of energy that you can get access to. So, that is the context in which we are looking at the ocean thermal energy conversion, or OTEC. So, in this class, for example, our learning objectives are to describe the principle behind the OTEC operation, what is the basic idea behind it, because actually from the energy that is available in the sea, you can actually tap it in multiple different ways. So, this is one of the ways in which you can sort of get energy out from the sea and put it to use where you would like it to be put to use. And in the context of how it is done, we will also look at what are the challenges associated with this OTEC technology, and also try to understand what are some, therefore related to those challenges, what are maybe some limits associated with it, or even some theoretical limits associated with it. So, this is the general context in which we will look at today's discussion. As I said, 2/3 is covered by water. There is a lot of energy that is available in the water, and at some fundamental level, just the way you talk of energy available in the wind system, the energy that is available in the water system is also at some fundamental level coming from the solar energy. So, sun beats down on the earth and then heats up the land, heats up the water, heats up the atmosphere, and because earth is a sphere, we have one side facing the sun, one side not facing the sun. So, in any at any given instant of time. So, clearly there are locations which are receiving a lot of heat, there are locations which are not receiving a lot of heat. This is simply based on the time of the day. On top of it, based on the latitude and the season, you will have some regions receiving less sun and sunlight, and more sunlight during winter or summer and so on. And as a result, there is a lot of variation of thermal energy across the planet, and there is a lot of variation of the thermal energy that is held in the water across the planet. This therefore results in differences in density in the water. So, you can have water moving up, moving down, you have a lot of water currents that are existing, and on top of it, so you can actually potentially capture energy from just these water currents, if there is a way in which you can do that. And then on top of it, there is also the temperature difference issue. So, if there is a way in which you can utilize the temperature difference between the region that is heated, and between water that is heated and water that is not heated, and that if that is energy that you can tap, then that is also something that you can utilize. So, the ocean thermal energy conversion, as the term indicates, you have the word thermal there. So, we are primarily looking at temperature difference. So, temperature difference is what we are trying to capture here. So, difference in T. In what I just discussed with you, there is a difference in temperature based on region that we have, but we do not have the ability to pick up the heat from the dark side of the planet and the bright side of the planet, and then capture that heat to run a heat engine. So, that is not something we are talking about today. So, there is another way in which there is a difference in heat that is held in the water. So, that is what we are going to look at. In technically, if you were out in a satellite, you could do that. In a satellite, you could have a dark side of the satellite, and the side of the satellite that is facing away from the sun and the side that is facing the sun. Potentially you could run a heat engine there and generate electricity. So, there you could just tap the hot side and the cold side, but there you will not have convective heat transfer, you only have radiative heat transfer. So, within whatever is possible there, you can actually do that. So, This is something that can be done, but in the planet that is too big a location for us to pull that off. So, we are looking at a thermal difference that is present in a much more local geographically local location region, but there is still a difference due to some other parameters. So, we will look at that, and on that basis the temperature difference is being utilized to generate electricity, to do bunch of other things, and that energy is being tapped. So, this is the OTEC idea. So, what is the idea here? As I said, it is not region difference, it is basically the difference in temperature between warm water at the surface. So, sunlight comes and we will see that detail there. So, at the surface there is warm water and much colder water that is approximately 1 kilometer below the surface. Okay. So, 1 kilometer is really not that large a distance, but in the context of water that may be significant. We will look at that in just a moment. But basically if you look at sea water, you have water at the surface and that is warm, and then there is significantly colder water about 1 kilometer deeper into the ocean. And so if you can pull that water, so you do not have to go to some other geographical location, you are in exactly the same location. In that same location, if you can pull the water from about 1 kilometer, so you basically have to put a pipe down, about 1 kilometer long pipe, and then pull the water up. Once you pull the water up, you have cold water available with you, and you also have warm water from the surface of the sea, and you can use those two to run a heat engine. And in that process, if you generate electricity, extract the heat engine, extract energy from that heat difference in temperature, that is what this OTEC is all about. So, ocean thermal energy conversion. So, this temperature difference between what is at the surface and what is much below the surface, about a kilometer below, is of the order of 15 to 25 degrees centigrade. Okay. So, this varies from region to region, there may be other factors contributing to it, but we are looking at a temperature difference of somewhere between 15 and 25 degrees difference. Okay. So, this may not be much, I mean it does not seem like much, and in fact it is not much. We will see some numbers relative to this. So, as opposed to the kinds of temperature difference that let us say engines in a car are trying to utilize, etc. This is not much, this is a much smaller temperature difference, much more modest temperature difference, even relative to say the temperature difference say thermal power plant is trying to use. This is not of that order at all. It is just that it is abundantly available. I mean it is just potentially just there infinitely available, and therefore can be tapped. It is of course renewable because it is happening in the time scales of in long, these are temperatures that are equilibrated in a very large body of material over a long period of time, and they will continue to keep getting equilibrated at those temperatures with the passage of time. So, what is the thermal profile of sea water? So, this is of interest to see because you understand what is actually happening in the system, and therefore understand the context within which we can tap this energy, for example. So, when sunlight arrives at the sea surface of the sea water, mostly it is the first 20 meters that absorbs sunlight. Okay. So, in fact even when you look down into the sea, I mean you will only find a few places where water is so clear that you can actually see a few meters down and you will see the sand below, right. Invariably it is kind of dark, after some few meters it is very dark. You do not really see anything. If you just stand at a beach and you see the water in front of you, you will see it light, I mean based on which part of the world you are, how deep the water is, and of course depending on how clean the water is, what turbidity is, whatever other factors are there involved in it, you will see a certain level of clarity in the water, but beyond that it becomes dark, right. So, it also means that the light just penetrates that far, and at that point it is all absorbed. So, the sunlight more or less in first about 20 meters of depth, which is not a whole lot, it is like say the depth of say 2 rooms that you may typically be using. So, in about 20 meters of depth the sunlight gets absorbed. Okay. So, this gives the surface some temperature. So, this temperature varies from region to region. So, at the extreme when you go closer to the poles, you have a temperature, the surface temperature of the water of the sea water that is there could be very close to freezing conditions, okay, or you may even be frozen or very close to freezing conditions at the poles. But if you go to some warmer regions, so Persian Gulf is considered amongst the warmer regions where the sea water is quite hot, you can see temperatures of the order of 36 degrees centigrade at the surface of the water, so in the sea water. So, at the surface itself, based on the region, you have a lot of variation, and this is primarily got to do with how much sunlight is arriving there, at what rate it is arriving there, in the sense basically what is the power it is delivering there, and if it is more obliquely inclined, at the poles that the power being delivered is a lot less, and you may not even get it delivered for 6 months of the year, and therefore it becomes very cold there. So, but then you have hot places at about 36 degrees C. So, now if you start in the 20 meters, whatever is there, that heat energy that has been captured there, then as a result of both the turbulence caused due to the mixing of that water, because you have now hot water and you have slightly colder water below it. So, there is some density variation, you start seeing some mixing going on. You also have a lot of when you go and stand in the sea, or when you go and stand in the beaches, you see all the waves coming to you. That has got to do with the interaction of the wind that is blowing and the surface of the water. So, that surface keeps getting churned up quite a bit by the wind that is blowing across. So, generally the water, both due to all the activity that is happening at the surface and all the to what degree that energy transfers downwards, variation in density, etc., you have a lot of mixing going on for a few hundred meters, okay, of depth of a few hundred meters. Significant amount of mixing is going on, starting both due to this energy that has come in from the sun, also due to the action of the wind on the surface of the water, etc. Considerable amount of churning around and mixing and what on is going on for the first 100 meters. So, first few hundred meters this happens, and then you have below that a boundary. So, this top layer is called the mixed layer, and from there you have a boundary. That boundary itself extends for a few hundred meters. Okay, so, it is not a very sharp boundary, but it is relatively sharp in the grand scheme of things, but a few hundred meters of boundary is there, in which there is this the level of disturbance comes down, and then below this boundary there is relatively undisturbed water. Okay, so you have first 100 meters or so which is very turbulent, and then few hundred meters you continue, you come through a boundary. Below that you have a boundary, and that boundary itself lasts a few hundred meters, across which this disturbance steadily cuts out, and then you at one point it becomes completely undisturbed. So, there is water below the boundary that is undisturbed. This boundary is called the thermocline. Okay, so, this boundary is called the thermocline, and below that you have water that is largely undisturbed and has been certainly not disturbed with relative to whatever action is going on top. So, this thermocline, it turns out that more than 90% of the sea water, exists below this thermocline. So, the volume of water below the thermocline is significant. So, the surface water which is disturbed and mixed up and having higher temperatures, etc., is actually a very small fraction of the total water that is available in the sea. So, in fact, that is only 10% of the water that is available in the sea, right, and all the 90% of that water that is there is now below the thermocline, where the temperatures are very low and of the order of 3 degrees centigrade. Okay, so, that temperature is there. So, very close to freezing temperatures, significantly below the depth of from the surface. So, if you go so maybe about a kilometer or so below you go, and then it becomes this cold. So, this thermocline is also quite important from various other if you read books related to say submarine and how submarines operate and so on. This is also considered kind of important from that perspective in terms of how sonar behaves there, how calm the water is or how disturbed the water is. All these things are related to the thermocline, and so this is also relevant from a military aspect, so to speak. We are not really looking at it, and that is not really the focus here, but for us the idea is that there is this layer below which the water is undisturbed, and this layer is called the thermocline. And more specifically, we have a temperature of depending on where you are, above the thermocline close to the surface you have a temperature of 36 degrees C, below the thermocline you have a temperature of 3 degrees C. So, in this case you are looking at about nearly 30 degrees, 33 degrees C difference, but this is like an extreme case. As I pointed out, mostly it is somewhere between 25 and 15 degrees C. On average, in fact, it is about 17, 18 degrees C across the water that you are going to see at various places, various coastal areas, but you can have anywhere from 15 to 25 degrees C difference. Okay, so this is clearly work that we have to do with respect to the sea, right. So, this technology by definition is something that is associated with the sea, with how you can operate something in the sea. So, what are the challenges there? right. So, and we are also looking at, as I said, we are trying to get water that is cold and find a way to interact with water that is warm, that is on the surface, and the process generate energy. So, you have to get that cold water, and that cold water is about a kilometer plus deep. You have to go further down, and then you get that temperature. So, so in fact, if you plot temperature, right, and depth. So, if you are at the surface, and let us say this is 1 kilometer and this is further down. So, you are looking at, say, let us say this is 36 degrees C, this is say 3 degrees C. So, you are looking at something that is like this. Some profile like that. Okay, this is just a schematic of a profile. The point being, it is not very linear, it is not a very linear profile, and you are going to see a significant variation of temperature in this region, and then virtually no variation of the temperature below. Okay, so here there is the lower region, not much in this region, right. So, the lower region there is not much variation in T, on top there is significant variation in T. So, it is certainly a non-linear behavior coming from top to bottom. So, now we have to work with water that is at the surface and work with water that is significantly below the surface, which is about a kilometer below. So, just to give you an idea of how complicated it gets working with the sea water, and especially water that is deep in the sea. If you look at what is people have explored the surface of the bottom of the seabed across the earth. Some kind of a mapping has been done to understand what at what depth you have the seabed, etc. So, the deepest point that they have seen in the seabed is the Marina Trench. Okay, so, the Marina Trench, this is about 11 kilometers deep. So, you have to go 11 kilometers deep into the sea to reach this point. It is somewhere near Japan, somewhere in that area it is. It is called the Marina Trench, and people got to know about this quite some time back, that they were aware that this place existed. So, if you take the last say 100 years or so, where people have tried to do various things in terms of exploration, trying to reach places that others have not gone to, etc., and try to push boundaries of what humans have achieved over the period of time. Then if you look at the Marina Trench, which is 11 kilometers deep, in all this time that people have worked on trying to get there with all the technology that has existed and so on, till very recently it has been visited by a total of 3 people. Okay. And these 3 people in fact did not even step out at this location. They were inside a particular kind of vessel, and they stayed inside that vessel, and that vessel basically reached this point, this Marina Trench. It reached the base of this location, and they were able to come to this point. So, they sat inside this vessel, and this vessel went deeper and deeper and deeper into the ocean. It went 11 kilometer deep, reached the bottom of this place called the Marina Trench, and they were essentially there. So, 3 people did this, 3 people managed to visit this place. It includes one of these film directors of the movie Titanic. He has visited this place. James Cameron, he is one of the people who has visited this place, so that is it. There are 3 people who have literally gone to this place. Now, if you contrast that with the moon, okay, you contrast that with the moon, that is 384,000 kilometers away, 384,000 kilometers away. Okay. So, not really half a million, but approaching that, approaching half a million kilometers, that kind of a distance. Okay. This has been visited by 12 people. There are 12 humans who have landed on the moon. Okay. So, 12 humans have landed on the moon, and not just landed on the moon, they were able to come out of that spacecraft. Of course, they were wearing a special space suit. They were not wearing our kind of clothes. They had a special space suit which moderated their temperature and atmosphere, that they could breathe normally, etc., because there is no air there. But they were able to step out of the spacecraft wearing that suit, walk around on the moon. Okay. So, 12 people, 12 human beings have set foot on an object that is outside Earth. These are the only 12 people who have ever done that. Okay. So, we have only explored the planet. These are the only 12 people who have 12 human beings who have ever stepped on any object outside of Earth, any other celestial object other than the Earth. So only 12 people have done that, but 12 people have done that. They have been able to land on the moon, they have been able to get out, walk around, even drive vehicles. They have had some lunar modules, something rovers they had, they drove those vehicles on the moon. They did various things, various activities that humans could do on Earth. They tried to mimic doing all those activities there. So this is 384,000 kilometers away. And you know the amount of difficulty it is. I mean, every time there is a rocket launch, people are so anxious that everything has to go right. So many technical challenges are there. It is by no means easy. Even to send an unmanned satellite to space, it is an extremely technically challenging activity. There are only a few countries even today, that there are only a few handful of countries that are able to regularly send unmanned satellites. India is of course probably one of those countries that is able to do so quite regularly, but still that is only a handful of countries that can do that. In that, the manned mission has literally been done only by three countries, in which only 2 have really prominently done it. Only one, China has just started doing it, but really only the Soviets and the Russian people or the Soviet Union and the Americans have been able to do manned missions on a regular basis, and in that only the Americans have managed to land on the moon. So this has been quite a complicated set of activities that are there, and that is very complex, very difficult, very challenging, and lot of danger there. Some people have died in the process of trying to land on the moon. In the very first Apollo actually blew up. I mean, the very first such rocket, which was on a test mode, basically blew up. I mean, or the people were trapped in a fire, they got killed. So it is quite a dangerous activity. It is hardly a safe activity. Despite all those challenges, despite the challenges of what is required to get out of the gravity of Earth, to pull out, do so many complicated things have to be done before you reach the moon. Despite all those challenges, 12 people landed on the moon. Okay, so that is a phenomenal accomplishment. But contrast that with the Mariana Trench. That is just 11 kilometers. 11 kilometers is nothing. I mean, 11 kilometers, if you were on a road outside, 11 kilometers would take you no point. I mean, if the traffic were flowing, you would probably cover 11 kilometers. If you were doing say 60 kilometers an hour, then every 6 minutes you would be doing 10 kilometers, right? So 6-7 minutes is what you are looking at to do 11 kilometers. I mean, something like that. In under 10 minutes on a road, in about 10 minutes time on a road, you would cover 11 kilometers based on the traffic conditions. So 11 kilometers is not at all a significant distance in the context of human activities. In the context of human activities, 384,000 kilometers is a significant amount of distance. It will take you forever to travel this distance if you had to do so. Still, 12 people managed to reach the moon, step out, walk around, do various activities. Only 3 people managed to reach the bottom of the Mariana Trench, and nobody stepped out. Nobody stepped. They just sat inside that vessel, looked out through whatever port was available in the vessel, and they came right back up. Okay, so they just took pictures from inside the vessel. They saw through the port, they flashed the light around, and then came right back. So this is all they were. So what is the challenge there? The challenge is the pressure or the pressure difference. Okay, so the pressure difference, that is the challenge. So what is the challenge? When you go from the Earth to the moon, even though it is such a complicated activity, so many dangers and so many difficult things involved, the difference in pressure when you go from the surface of the Earth into space is 1 atmosphere. Okay, so difference in pressure. So Earth to space. So one difference in pressure, meaning when you are on the Earth, you have 1 atmosphere of pressure that you are experiencing, that when you stand you experience 1 atmosphere of pressure. If you just lift off from Earth and come out into space, there is essentially vacuum out there. So there is the pressure has dropped to 0. So you are used to 1 atmosphere pressure, pressure outside is 0. So whatever vessel that you create, whatever spaceship you create should maintain 1 atmosphere pressure inside the spaceship while facing 0 atmosphere on the outside of the spaceship. So the wall of the spaceship will see 1 atmosphere inside, it will see 0 atmosphere on the outside, right. So that is the difference. So difference in pressure across the wall of that spaceship is 1 atmosphere. It has to see 1 atmosphere inside, 0 atmosphere outside. So that is the difference, and that spaceship should stay intact in that difference. It should not break up, it should not explode. You blow air into a balloon, why is it expanding? It is expanding because the pressure inside is more than the pressure outside, or at least it is initially, if you just maintain it like that, pressure is higher, so it expands till the the air pressure outside as well as the the elastic properties of that balloon together counteract the pressure inside. So, that is how it takes some shape, but if the balloon is weak it will explode, right. So, that is because there is a pressure difference between inside and outside. Same thing, if the space ship which is a manned mission should enable people inside to live. So, it has to have oxygen, it has to have, if it is just air, it has to have a mix of oxygen and nitrogen, and the pressure should be 1 atmosphere. If the pressure is too low, you will be struggling to breathe. So, pressure should be 1 atmosphere because our body is used to that pressure. Outside is 0, so that pressure difference across the wall of the vessel is 1 atmosphere. Now, from surface of earth, into sea, okay, 1 atmosphere per 10 meters. Okay, so, remember it is not just 1 atmosphere pressure difference, it is difference of pressure is 1 atmosphere for every 10 meters that you go into the sea. Okay, so, you start at the surface of the sea and you go down 10 meters depth you go, the difference in pressure is 1 atmosphere. So, your body is now used to 1 atmosphere, but the pressure outside is 2 atmospheres. Okay, so now if you want to compare a spaceship that has landed on the moon with something that is underwater and you want to create a situation that is very similar to a spaceship sitting in the moon and a underwater vessel. So, what is the situation? The pressure difference across is 1 atmosphere and pressure inside is 1 atmosphere. So, in the moon pressure difference is 1 atmosphere between inside and outside and the pressure inside is 1 atmosphere. In the sea, if you go down just 10 meters, you have recreated the same situation, except that the pressure outside is excess, there the pressure outside is 0. In the sea you just go down 10 meters or anywhere, even in a deep enough swimming pool, if you go down 10 meters, your body is feeling a pressure of 1 atmosphere of air and 10 meters of water, that 10 meters of water is equal to 1 atmosphere of air. So, 2 atmospheres you are facing, right. So, just 10 meters down the vessel already faces the same situation that a vessel that has landed on the moon faces. So, you can now imagine if you go down 11 kilometers, okay. So, 11 kilometers is 11,000 meters and it is 1 atmosphere for every 10 meters. Therefore, pressure difference is, total pressure difference is 11,000 divided by 10, more than 1000 atmospheres. The difference in pressure between the inside and outside of that vessel is more than 1000 atmospheres. So, that is why even though this is only 11 kilometers and technically on a straight road you would reach this in about 10 minutes time, you would never do it in 10 minutes if you were going under the sea, and the pressure difference you face is 1100 atmospheres, that is 1000 times more difficult from just the pressure of perspective of pressure. This is 1000 times more difficult to handle than than landing on the moon. Okay, if you do not look at any other technology, there are other technologies change the scenario completely. I am just saying with respect to pressure, going 11 kilometers under the sea is 1000 times more difficult than reaching the moon. Okay, so that is the point, and that is the reason why this is a problem. And the OTEC technology requires you to deal with water that is at least 1 kilometer down. Okay, so therefore you have to send a pipe down there, 1 kilometer down you have to send a pipe. You have to work with the fact that there is water is moving, the top water is moving, there may be some currents of water below. So, you have to work with all that. Okay. So, so there is a lot of challenge associated with dealing with water. Pressure is a major challenge, depth is a challenge, water currents are a challenge. So, these are all extremely difficult to deal with, and therefore, OTEC, even though people have been working on successful demonstration that has lasted a period of time, have been very few where they have managed to actually work with it. Okay, so what is happening here? So, you have as you recall 175 petawatts of energy coming from the sun. So, that arrives into the sea and then it heats up the top surface of the sea. So, we said say let us say this is the top 20 meters. So, if this is 1 kilometer, so top 20 meters is a very thin layer. So, in this context this is a very thin layer. So, we are looking at this is 1000 meters. So, this is 1000 meters. So, so basically 10% of this would be 100 meters. So, you are looking at 20 meters which would just be this much. Okay, so, to the first 20 meters is where you are having much of the heating that is going on, and then below that you have actually several hundred meters over which things are cooling down, quietening down, and then when you go down 1 kilometer down, everything is quiet. So, this is 1 kilometer, and that is where you have this temperature difference of 15 to 25 degrees centigrade. So, what are we doing? In principle, this OTEC system, which is what we have here, simply takes water from the surface of the sea and water from deep below, and both of them arrive here, and with this we generate electricity. So, this is the basic idea of the OTEC. So, you have picked up water. So, you readily got this, and this is in large supply. That is the whole attraction to OTEC is that if you go to any coastal area, this is available to you in large supply. You can keep pulling up this water. I mean, you just have to put 2 pipes. In that sense, it is a very simple technology. You have to have 2 pipes. One pipe will be at the surface of the sea, another pipe has to go deep down, that is it, and then you have a pump to pull up the water from deep below, and that will get you the cold water, pump to pull up the water from the top, that is a warm water, that is it. You already have all this, you do not have to put in any thermal energy, you do not have to burn coal or do any such thing to generate your energy. So, it is very clean in that sense, very clean, you do not have to do any major thing. So, this is the 2 things that you have got. But having picked up this cold water, there is actually a bunch of different things that we can do. So, it is not you should not see the OTEC plant in isolation, because actually many things can be done once you pick up this cold water, cold sea water that is coming from about a kilometer down. So, in a sense, when you look at the OTEC process, you should look at it in totality, you should try to actually do all of the things that are possible with the OTEC system. And then you can fully benefit from it. Okay. So, but now for example, this is what we are at the top level, this is what we are doing, we have picked up cold water from the bottom, we have picked up hot water from the top. So, now let us look at efficiency. So, it tells us that if you want Carnot cycle efficiency, you have 1 minus T2 by T1 is the efficiency that we can get, is the best efficiency that we can get. So, that is we have let us say 5 degrees centigrade that is down here. Let us say it is 5 degrees centigrade below, and let us say this is 25 degrees centigrade on top. Okay, so, 5 degrees centigrade in the cold water, that is significantly below, and 25 degrees centigrade on top. Those are numbers that I told you, roughly similar to numbers that I just mentioned to you in this context. So, we have to this T2 and T1 have to be absolute temperatures. So, in Kelvin. So, that is 278 Kelvin and 298 Kelvin respectively, right. So, 1 minus 278 by 298. So, if you do the calculation, you will arrive at about 6.5% roughly. Okay. So, that is like the best that we can get. So, in fact, mostly we are not even doing this, we are really actually looking at values of the order of 3% of something like that. That is more the practical kind of efficiency that you get out of an OTEC plant. So, that seems like remarkably low. I mean, even if you look at our worst case scenario of solar energy, that we are looking at 5% efficiency, that is like our worst case. This is the best case or typical case is 3%. In solar energy, you are looking at 25%, and then you say that that is also not good enough, you want to do better than that. So, a lot of things we are trying to do there, and we are looking at a hypothetical case where you can even get 80% efficiency or something like that, right. So, you are considering all those options. Here you are looking at 3%. So, this seems like a complete waste of our time to do this. But the advantage, as I said, is that this is very easy to do, and there is abundance of this available, and it is very not at all complicated to set this up in the relative sense of the activity. There are a lot of side benefits to it and so on. So, therefore, people feel that even if it is only 3%, if you are just like that going to keep getting it, I mean if you are just going to get it without much effort and you are just going to steadily add to the energy stream, then let us add it everywhere. Because in general, what you are going to see is, if you look at the entire energy scenario internationally, it is unlikely that any one solution, we are also seeing a whole bunch of solutions here, it is unlikely that any one solution is going to completely take over from everything else. It is very likely, on the other hand, to have multiple different solutions which will serve various needs locally, will also add to the global pool of energy that is there and so on. And many of them have side benefits, many of them have side disadvantages. So, we have to keep all of that in context when we look at any one technology. So, nothing is going to be an all conquering technology. So, in that context, this is also okay. This 3%, just that all, I mean pretty much any coastline, anywhere you can try and capture this is something that is a great plus, right. So, therefore, this is, so efficiency is about 6.5% at best, and then you are actually looking at about 3% more likely. So, what can we do? I mean, having picked up the cold water, one thing that we can actually do very easily, straightforwardly, is air conditioning. Okay. So, in fact, if you look at the air conditioning plants, if you look at AC plants at various buildings, when they do centralized air conditioning, when they do air conditioning of multiple buildings using one plant, which are distributed buildings, many times what they are doing is cold water is being sent off to different places. So, one place only the plant operates and creates cold water, then that gets sent to different places. From there the local heat exchanger will then eventually make that building cold, etc. So, so things like that are being done. So you transport this cold liquid to different locations and then work on it. So here you already got the cold liquid, you got 5 degrees centigrade or 3 degrees centigrade liquid, you just pulled it out from the bottom of the sea, it is sitting there, you just pulled it out from there. So it is there. So if you are if you set up a network ahead of time, so imagine a coastal city in let us say in Tamil Nadu. In Tamil Nadu, for example, I am in Chennai. Chennai is very hot. In summer it is very hot. A lot of people struggle with the heat. It is very hot and humid, and so there is a great need. I mean, lot of people really feel the need for air conditioning. It would be extremely uncomfortable to operate and function during the middle of the day without air conditioning in many places in Chennai. So that feeling will be there. So we are putting air conditioners. But now if you have cold water from the sea, so for that lot of electricity is being used. So the electricity usage in Tamil Nadu or in Chennai at least will go up significantly in summer because of the number of air conditioners that will switch on during summer. So significant use of electricity, so significant use of energy. So now in the process of generating electricity, you just pulled out cold water from the bottom of the sea, and if you actually had a network of pipes which could transport this cold water to various places in the city, you can actually technically do air conditioning using this water, without having to put air conditioners in the conventional sense of the word, where you have a compressor and a lot of different things that are going on and lot of electricity being used. You already have this cold water that is available, with which you can appropriately design your air conditioner to deliver this cold air to various places in the city. So technically to various buildings in the city, for example. So technically we can have air conditioning that is significantly dependent on this 3 degrees centigrade water that we are getting off the 3 or 5 degrees centigrade water that you are getting from the bottom of the sea, where essentially your main energy usage is that pump that is pulling that water out, right. So that is a major thing that you can do associated with this OTEC plant. Of course, the purpose of it is electricity. So that is one major activity that we will anyway do. So there essentially what you are doing, we will talk about how the electricity is generated in just a moment. So that is one major output from this OTEC plant. So air conditioning would be like a sort of a byproduct of this plant, because you can do it, and then electricity is your primary product. Desalinated water. So in the process of doing this electricity generation, one of the ways in which we do it, there are a couple of different ways in which we can do it. I am going to talk about that. But one way in which you would do this desalination, would do this electricity generation, would result in desalinated water being available to you. That of course can be used both for drinking as well as irrigation. I mean again, if you look at the Chennai situation, water is also a major issue, like with any major city. Like with major cities, increasingly now in the news you hear about cities which have either run out of water or just on the verge of running out of water, and for example they say in Bangalore is one of the cities which is likely to run out of water. So the scarcity of water is a significant issue, and many cities have that problem. So Chennai also has a problem with scarcity of water, and depending on where you are in India, you will have differing levels of water scarcity issues through the year, or even internationally many cities have this issue, because populations have grown and they are concentrated in some area, and you have to have water available to them. So if I mean, of course you may depend on rain, or you may depend on rivers, you may depend on some perennial rivers, you may depend on glaciers, etc. This is one way in which you can get the water, where you are getting electricity, at the same time you are also getting drinking water by doing because the process of getting the electricity is creating desalinated water for you, right. So you can get that, so you can get drinking water, you can use it for irrigation, and to some degree whatever cold water remains, you can actually do mariculture. So where it's sort of running farms where you allow sea animals to grow, and you can use them for various purposes depending on what you are interested in. So as you can see, there is a wide range of things that you can do with this associated with this OTEC process, and they are all associated with activities that we are anyway already doing. Air conditioning we are already doing, some amount of usage of sea related products we are already doing. Water we need, irrigation we need. So, all these things are already there, electricity we need. So, all these things come together with the OTEC plant, and therefore, this OTEC plant is a good thing to have, despite the challenge of having to deal with the depth of water and getting the pipe to stay together. So, once you get all this cold water and the warm water, what do you do? So, there is one way, there are two different ways in which you get this electricity out of it. At the end of the day, you have to run a turbine. So, if you just have water sitting at 36 degrees C, that is just flowing, I mean you cannot really run much of a turbine with water sitting at that temperature. You need basically vapor pushing through the turbine and getting the turbine to run. So, normally what is done is you can set up a low pressure situation, so that the water now comes out in vapor form and then is able to run the turbine. So, warm sea water will evaporate at low pressure and it will run the turbine. Then it will be condensed by the cold sea water, and you will have some water you can inject. So, this warm water which first got which evaporated is now clean because it is in vapor form. So, the salt is not there in it, and then when you again condense it, you can actually have desalinated water. So, you remove the salt separately and then you get this desalinated water, and so that desalinated water becomes available as a byproduct. So, when you do this open cycle method of getting electricity out of this OTEC plant, you get desalinated water as a byproduct. Another way in which you can do it is to run this closed cycle operation, where basically what you do is you do not use the water directly to run the turbine. Instead, you have a closed system where you actually have a low boiling point liquid, typically ammonia is used. Any other refrigerant could also be used, but with refrigerant we have already had this issue of how the refrigerant creates this hole in the ozone layer. So, many refrigerants are now banned. So, there are only specific refrigerants that are permitted to be used, and so in that context you have to be careful what to use. But for example, ammonia would be something that boils at minus 33 degrees C, and so you can use that in the context of this system, and then that would be the liquid that would evaporate, that will run the turbine and then be condensed and etc. So, again warm water will make it evaporate, it will run the turbine, and then cold water will condense it. So, this kind of an operation we can think of. So, we have an open cycle and we have a closed cycle. We would also keep in mind that you are pumping in large amounts of water. So, everything that comes with it. So, it is not going to be like clean water, you are going to have you may even have some small sea creatures that show up, and various things that are available in the sea will show up. So, in some sense yes, you may do some disruption to the marine environment that is there, and the water that you are ejecting is ejected back into the sea. So, you are doing some little bit of churning of the sea water in this process, but the general calculation shows that at least with respect to the water, I mean the quantity of water we are going to use is so minuscule relative to the amount of water that is available in the sea, and we are basically just putting it back. So, whatever churning that we are doing is so tiny that it would more or less have no impact even if you did large scale deployment of this OTEC technology. Okay, so, if you did large scale deployment also, we would not have much of an impact on the behavior of the water and just because of our interference in it. But we would always be cautious, because this is how we thought about the atmosphere, and we said what can we do, we are not going to do anything on earth that can disrupt the atmosphere, but we are currently doing that with respect to the CO2 emissions. But in this case it seems like the calculation shows that you can use significant amount of OTEC technology across the world, not really make a big difference to the water itself. However, we may impact the marine life that exists there, because they are accustomed to certain temperatures at various regions, and if you keep on pumping in, pulling out water, you are probably disrupting the creatures that are that depth, and you are pushing back water at some other level which has a different temperature. So, you are affecting creatures at that depth. Again, that is close to the shore. So, if you go away from the shore, this is not going to be an issue. You can even have offshore platforms which are basically like a ship. So, in the ship some of the, even right at the early days, people tried all of this. They put a ship out there, and from the ship there would be a pipe going further deep down, pulling out the cold water and then doing all the electricity generation. But all of these have been challenging. Many of those ships have been destroyed in the ocean. So, that has happened. Even in India, one of the plants that was put up in 2002 in Tamil Nadu, it was put up. It had issues with the cold water pipe line. So, it was partially successful, but not, they could not sustain it over a period of time. They had some issues dealing with the cold water pipeline. So, even in the coastal area there is a problem. Even offshore, when the setup is made, there can be challenges. So, it is not an easy technology to work with because you are not on solid ground. I mean you are dealing with liquid that is and you are dealing with depths, liquid flowing in large quantities that we do not have enough control on. So, that is something that we have to worry about. So, in conclusion, OTEC is available to tap in almost all coastal regions. So, except if you go to extremely cold regions, then you may not have big difference between the surface temperature and the temperature of the water much further down. So, that is something that we can think of, but most other coastal regions this can be done, and as I said, you can do in large scale, it does not make a big difference. It can be set up in an offshore mode as well, just the way you have offshore oil rigs, right. You have offshore oil rigs which are sitting floating platforms sitting out in the sea. So, they would have to figure out at what location they are able to access the depth of water easily. So, a lot depends on how the sea shelf is and what is the topology there, because there are places in the if you examine the coast, depending on where you are, the water will sometimes drop off, the depth will suddenly increase dramatically. There are other places where the the ocean floor is quite shallow from the say the coast. So, you start at the coast, you can actually walk quite some distance into the water and you will still be only knee deep or waist high, and you can still see if for even for further distance the water is just maintaining that kind of depth. So, many of those popular resorts that are there which you see beautiful photos of are all places where this kind of a situation is there, where the depth is very shallow for a long distance. So, you can get into the water, but you are not in any deep water for a quite some distance, very visible distance you can see it. But many other places, for example, in Chennai, in and around Chennai, a lot of people say that the water floor falls off quite dramatically even if you go a little distance into the water. Therefore, it is not safe to go unless you know what you are doing. It is not at all safe to just wade into the water beyond some very short distance. A lot of people do not realize the risk there, but that is a safety issue that is there. So, the point being the depth from the coast from the surface can change significantly from location to location. So, in some places you can have an onshore setup which can be which is the typical way in which you would probably think of an OTEC plant, because you can have the whole plant sitting on the shore and just a pipe that goes out into the water, because in a short distance the pipe can just drop down, in great depth it can go down, and then from there you can pull up the cold water. There may be other places where you have to go quite a bit away from the coast before the depth in water is significant enough, right. So, then it does not make sense to start at the coast and send a pipe which goes long distance at the floor and then eventually goes down. So, it helps there to actually have offshore platform where like an oil rig you are just sitting this whole platform is sitting out in the sea and you just have a pipe going vertically down. Then that will be an easier pipe to put together and manage. So, it goes straight down vertically down to that location which is as deep as it can get, about a kilometer deep, and then from there you can pick up the cold water and then the warm water is on top. As I said, the efficiencies are low, it is only about 3-4%, functionally you are only getting about 3-4%, but that is adequate because you can actually do I mean you are just more or less getting it for free, there is nothing of any great significance there, and it is clean. You are except for the fact that you are churning up the ocean and you are getting a lot of marine creatures or marine organisms out, which could be significant if you are doing this in a large scale over a period of time. There is no emissions as such, it is basically a clean kind of energy, and therefore that is fine. And then the big challenge there is the stability of the structures in the presence of water and water currents is a factor that you have to address. Even the all the piping and whatnot, you are using salty water, so you have to make sure that corrosion is not an issue. It is not just the salty water, it is flowing salty water. You are pulling up water, pumping up water, so it is going to flow. So, you are also going to have some abrasion of the surfaces, and so the materials should be such that they are abrasive resistant and they do not corrode even if there is abrasion and you have this salty water conditions. So, these are all some of the challenges. So, that is the overview of the OTEC technology. As I said, it has been deployed at some few places in the world, it has been tried in India, and I think more attempts are going to be made because it adds an interesting mix to the energy scenario. Some places it will make a lot of sense to have, may not be in every location, and to the degree that it makes sense, it is worth trying. Okay, so this is what we want, I would like to discuss in this topic and gives you a reasonable overview of this technology. Thank you.